technical difficulties with the iPad, but I got a new iPad, so we're all set. And I thought we'd just start this chapter off with just the basics. We're going to go over the mechanisms, everything you really need to know with the basic reactions, and then we'll just kind of build upon that. And then by Tuesday, we'll have every single reaction known, and then you just use those reactions to do synthesis and problems on his exam. So the first reaction we're going to start with is hydration. And what better organism to represent this mechanism than Squirtle? And much like Squirtle, you guys are starting out in your first form. And via these videos, you're going to reach your final form, which is going to be Blastoise. But we got to start from the beginning, which is the hydration mechanism. So how does this work? Well, H+ gets grabbed by the oxygen. That's then going to form this intermediate. This can then resonate up, and this oxygen can actually attack that open orbital, giving us, this is a reversible step, this intermediate. And we have a positive charge on this oxygen. And now then what's going to happen here is this hydrogen can donate its bond in, and then we can have a generic base come and grab this hydrogen, giving us our final product, which is going to be this bad boy right here. And just like that, we made Squirtle proud. Let's give him some little sunglasses real quick. Oh yeah. We made him proud. Okay, so moving on to the next mechanism. You got one down, you understand this one. With this mechanism, we can now build upon it to actually learn the acetyl formation mechanism, which is the mechanism you're going to have to know for the exam. I guess past Ross put in a little hydrogen right there already. But I was going to draw that in. I don't like that there. So how does this mechanism work? Well, just like the hydration, oxygen will grab a hydrogen, and this hydrogen actually comes from H2SO4, so it's either H+ or H2SO4. H2SO4 is a strong acid, so that can act as an H+. So just think, if you ever see H2SO4, it's the same as H+. But once again, oxygen with its lone pair is going to grab this hydrogen. It's going to give us this intermediate. We can then resonate this up. Ethylene glycol can come in. Now he is a thick boy, so watch out. He will come in and attack this carbon right here. Once again, reversible steps. Comes neutral. Ethylene glycol comes in. There is a positive charge on this oxygen right there. I do want you to know that. And we can actually do what's called a skip step here. So we can use the lone pair from this oxygen to actually come and grab this hydrogen. This hydrogen can donate its bond in. That can then lead us, once again reversible, to this intermediate. And now then we have ethylene glycol here. It is neutral now. This can then leave. That's going to open us up an orbital. This orbital is now open. That's giving this oxygen permission to land right up in there. Once again, reversible. It's going to give us this intermediate right here. And this oxygen is positively charged, and boom, here comes that generic base. This hydrogen is going to donate its bond in, and this generic base is going to grab this hydrogen, and that's going to actually give us our final product and take up majority of my iPad screen, which is this. And to make it easier, I will label these Step 1, Step 2, Step 3, Step 4, Step 5, Step 6, and finale. So, not now. We do not want to finish that on my iPad. That is the final product. So, moving on. We got some more examples here. This is actually a reverse acetyl formation. So this one's more challenging. I'm going to give you guys a few seconds, see if you can figure it out. Okay, I think that's enough time. Let's see if you guys figured it out. So once again, we see that H+, and I'm just going to actually draw it this way. It comes in and grabs it. You can choose either one. You could choose this one if you want, or you could choose this one. I just prefer to choose that one. That's going to give us this intermediate right here. This oxygen does have a positive charge on it. Do note that. And what's going to happen here is it's going to leave. That's going to give us this. Which is actually an open orbital right here. H2O is going to come in and attack. When H2O comes in and attacks, MEOH, positive charge on the oxygen. We can actually do the skip step here. Donates in. Oxygen grabs its hydrogen. It's going to lead us to our next step, which is this right here. Oh man, my bad. Didn't mean to do that, guys. I like to draw it like this so you can actually see the bonds. Positive charge on that. Oh, that is kind of squiggly. You see the deal. This can now leave, and since this is a reverse, we're actually going back to a ketone. So there's actually a lone pair on this oxygen, which can form a double bond right there. And you're going to get this intermediate. And once again, here comes our boy, the generic base, grabbing that hydrogen, giving us our final product. And just like that, it is complete. And to make it easier, I'll label it again. Step 1, 2, 3. There you go. Moving on. More examples continued. So since we have excess of this, you want to know it does add on twice. And the mechanism, once again, is the exact same as all the others. And it's going to take a while to do this. So I'm going to try and rush through this mechanism. Actually, you know what? You already saw the mechanism. So just predict what happens here. Because that would waste a lot of time, since I already showed you this mechanism. Because it does the same mechanism as a hydration base. Actually, you know what? I will show you the mechanism, because it is a slightly different. I don't want anyone to be lost, so I am going to show you the mechanism. My bad. My apologies. Oxygen comes in, grabs hydrogen. This is now positively charged. We can now have some resonance occur up into the oxygen. And this oxygen can now come in and attack at that carbon. OH. OMe. H. Positive charge on that oxygen. This oxygen can now grab this hydrogen. It can donate into that oxygen. leading us to our next intermediate, which looks like this. This can now leave, giving us our next intermediate. Another MeOH can then come in and attack positive charge on that oxygen. Sorry I'm drawing small, guys, but I don't have much space on this iPad, to tell you the truth. And here comes our boy, generic base, grabbing that hydrogen, and the hydrogen does donate into that oxygen, and that then gives you your final product, which is what we already predicted. This. And that's not a double bond, that is a single bond. A very poorly drawn single bond, but it is a single bond. And that's the mechanism for this. So, moving on to the Grignard reactions. Now you're going to run across two Grignard reactions, either ionic or the classic. And they both follow the same rules and concepts, so don't worry. Now, ionic might just look a little different because it has a metal attached to a carbon, but once again, it's the same as a Grignard reagent. And we're going to look at how to utilize these. So let's take a look real quick. So, Grignard reagent, really easy actually. Find your aldehyde or your ketone, resonate it up, and then, oh, I didn't even attach anything to this Grignard. Okay, there an ethyl. Then grab the bond from Mg, attack the open orbital, and if there is no then H+, keep the minus charge on that oxygen, and then just attach the bond from the Mg on there. And that's your product. For the next one, same thing. Resonate up. This is actually methyl, so then just attack there. That's what's attached to the MgBr. And then since we have then H+, the O- actually becomes OH. And that gives you this product right here. Now then, if we have an aldehyde and a ketone, or we have two ketones or two aldehydes on a single molecule, it gets a little complicated because then we can't actually do a Grignard reaction unless we protect it. Now, how do we protect these bad boys? Well, give me some ethylene glycol, and that's going to react with my aldehyde. And don't forget your H2SO4 right there. Yeehaw. Okay. There you go, right there. Boom, bada bean. Get that. Now then, react this with MeMgBr. And like I just said, it just resonates this up. And the Me attacks there because it's not going to attack this bulky boy right here. So I'm actually running out of some room right here. So let me move this guy over right here. And let me draw him out real quick. You guys can see. It's kind of like art class, but a lot more stressful. And since we don't have then H+, got that minus sign on there, and methyl. And if we reacted this with H3, we'll go through that in synthesis because I'm just focused on Grignard reactions right now. I don't want to confuse you guys. But that'd be your product here, and that's how you protect and then add Grignard reagents on when dealing with an aldehyde and a ketone. Now, moving on, my friends, we got another example here. Once again, resonate that up, locate the bond. This is ionic, but follows the same rules as the Grignard. So take this bond, attach her on over there. Draw out your base structure. And then since we do have an H+, this is a hydrogen right here, Keep it. And that's your product. Now, how do we craft molecules using Grignards? Well, much like Minecraft, you got to start from the basics and you got to build it up. And Dr. Paul does like using synthesis, so you are going to start from a basic molecule and you're going to use some Grignard reactions in order to build it up. But how do we do that? Well, first you add a halogen to the compound, then you react it with Mg, and then you react it with an acetyl. And let's take a look at this, see how this is done. So Br2 reacted with the benzene ring. If you remember this from last exam, we can add it on anywhere in the ring because we don't have any electronics dictating where it has to go yet. So let's put this bad boy on right here. React that with Mg. It's going to attach on to the Br. Just like that. Let me screw in my pen tip real quick because it was coming a little loose. And once again, now we're just back at the basics. Look at this. Boom. Boom. And we did not have H plus yet, so we just have that minus. And to save some space, I'm just going to say that's pH. pH is a benzene ring. Do you recall that? And then since we have H plus on here, boom, bada bing, that's going to give us our final product, which is this bad boy right here. And that's how you synthesize using Grignard reactions. Now moving on. Grignards with carboxylic acids. My arch nemesis. I'm just joking. Okay, so how do these work? When you just have a regular carboxylic acid, recall that Grignard reactions can only deprotonate the OH. So the only thing that's going to happen with this guy is this. Even if we have excess, it can't add on. It's physically impossible because the negative charges, you have to, if we do resonate this, you would get an intermediate that looks like this. And this is no bueno because we have two negative charges way too close to each other. So even if we do have excess MEGBr, the only thing it can do is deprotonate when we're dealing with just a carboxylic acid. Now when we're dealing with a carboxylic acid and a ketone, if we have one equivalent, the only thing it's going to do is, once again, if there's only one equivalent, it deprotonates first. That is always what it does first. Whatever it can deprotonate, it's going to deprotonate. And I didn't even draw a deprotonation. I don't even know what I was thinking there. There you go. There you go. So that would be the product of this one. If we have two equivalent, however, we deprotonate. And we can attach on at the ketone. Just like that. So pretty simple stuff. Just some rules to follow. Grignard. Wait, did I skip something? Oh, I definitely did. Yeah. Thank goodness. You guys need to know this. Grignards with esters. They usually add on two equivalent Grignard reactions. And I'll show you why. Now, the first reason why is, once again, we know the basic mechanism of Grignards. Then attach that bad boy on there. You're going to get this intermediate right here. And then since we have then OH, we'd have that. And then put on that ester. However, the ester can then also leave. And then you can actually add on another Grignard, giving you methyl, and OH. And that's actually your final product. When you have excess, of course, if you only have one, you can't add on two things if you only have one equivalent. That's physically impossible. I mean, you can try, but I think the world and universe are going to go against you. Okay, looking at the next one. If we got a cyclic compound and we're dealing with esters, how does this work? Well, once again, it's the same mechanism and the same rules. Attack first. Oh my gosh, I forgot to make it cyclic. I just made a benzene ring. There's an oxygen there. Methyl. OH, because there is a then H plus. And now then, we're going to break this ring. And we're going to have another methyl come in and attack. And that's going to give us this actually, and then since there is H plus present, that oxygen would take one. And this is actually a product. That is methyl, not nethyl. I know it looks like an N, but that is an M, and that is an M. And that's your final product. Pretty simple stuff. It all kind of follows the same rules, and all kind of blends together. Now, moving on to Grignards with acid chlorides. Now, how does this work? Once again, do your first step there, then attach this on. And since we do have then H plus, it would be that, and then I'd have this, and this is R, which is just a carbon chain, and then Cl. Now, if you guys recall, chlorine is a good leaving group, so this can actually leave, and we can actually have, here comes round 2, and for the KO, attach. And that would then give us our final product, which is I apologize again, there's not much room to draw these. This is your final product. So, just think of it this way. Do your Grignard reaction first, attach on the first Grignard reaction. If there's excess, then just however many leaving groups you have, make them leave, and attach on however many more Grignard reaction or Grignard reagents you have. So for the next one, we have 2 leaving groups, and we have the double bond, so we know there's going to be 3 times of these adding on. So overall, looks kind of crazy, but that's your compound, it's your molecule. And that's just from counting 1 leaving group, 2 leaving groups, and then a double bond 3. So 3 Grignard reagents are going to be added on. And moving on, Grignards with Amides. Now, oh, wow. Did not mean to already have the answers. Ignore those. Look away. How dare you look at that work? I work through these before I actually do them. Okay. So, looking at these amides, it basically follows the same reaction. Boom. Then add on your Grignard, which is pH in this case. And then since we do have then H plus, now the only time these get a little different is when you do secondary reactions with these. And this is what I mean by secondary. This is your second reaction. So the first step is going to be the same. And then since I did kind of change it up and I did say no H plus, this would be minus. This is your amide right here. And then put on your pH. Now then if we react this with H plus and H2O, just get rid of the amide and resonate this down. And that's your final product. So basically it's like a reversion mechanism of the acetyl formation. However, this time we have an amide in there. And the amide is going to kind of act like a leaving group. And this is not the real mechanism. The real mechanism is way more complex, but you don't need to know the mechanism. You just need to know what happens in order to get a good grade, okay? So this is what we're going to leave it at. And moving on. Okay, we got one more Grignard reagent with an amide. Let's look at this bad boy real quick. Same thing's going to happen here. I'm going to say then H plus. Once again, I don't know why I have to ignore that. I forgot to put in then H plus. So then we have OH here, NME2, and our Grignard reagent add-on. Now, if we add this with H plus / ETOH, it is kind of like an acetyl formation. However, instead of an acetyl formation with just an ketone or aldehyde, we now have an amide in here. And how I like to think of this is, don't look at the real mechanism. Amide leaves, OH leaves, and then if you have excess of this, you will have 2 of whatever the ETOH, MEOH, whatever is attached to the OH, add on here. So then you would get this product right here. Try and color code these for you. Red is leaves, add. And once again, that's not the real mechanism, but that's the easiest way to think of this because you don't need to know the mechanism for these. You just need to know what happens. And for Grignard reagents, that